It's a great pleasure for me to welcome. I don't usually do JQI introductions, right? So because I kind of invited Monika because we are working on a problem together. I actually met her just a minute ago, and I was very impressed by our exchange. She had a lot of questions on the theory, which I can tell you is not usual from experimental colleagues. Okay? So she is at Munich. I guess it's a Max Planck Institute and LMU kind of joint faculty position in this huge group that Emmanuel Bloch leads. And she's in charge of some of the machines there. And she did her PhD in that group, then went off to the other great laboratory of atomic physics in Europe, the École Normale, in Aidelsburger, and now she's back in Munich as a, I guess it will be equivalent to assistant professorship in the United States, in the same group where she's leading one of the machines, which is doing synthetic gauge fields, a subject very popular here, but a subject even much more important than that, many-body localization also, which is where I overlap with her. So she's going to tell us, she chose the synthetic gauge field subject because that's, I think, that's really a more popular topic in JQI and something I'm looking forward to learning. And so I'm not going to say anything more, and I'm going to let her give a talk.
Thank you very much. Thank you very much for this nice introduction. I'm very happy to be here. It's my first time visiting JQI. So there are many interesting people and groups I'd look forward to talk to. I don't have a faculty position yet. I'm applying for one. I'm hoping to get one soon. But I'm kind of a senior scientist at the LMU University. So I am actually supervising some of the labs of Emmanuel Bloch and starting my own group there. So I've chosen to talk about synthetic gauge fields, which I've also worked on during my PhD. And I would like to give you a kind of overview of what we did there, where we think we stand in order to use these techniques in order to study many-body systems, since most of the things we have done so far were in non-interacting systems. And then in the end, I would like to tell you about more recent results in making these fields dynamical. So just to get everybody on the same page, all the experiments I'm telling you about are with bosonic atoms in square lattices. As you know, we like these systems very much because they are well isolated from the environment. We can control the tunneling parameters, the interaction parameters in this Hamiltonian. And our main goal was to kind of extend or find new ways in these optical lattice potentials in order to study topological many-body phases. And this is most of the part of my talk that I'm going to tell you. Basically, our technique is based on Floquet engineering. What does that mean? It means that we take our lattice Hamiltonian, we parametrically vary some of its parameters in order to create a time-dependent Hamiltonian that is periodic with a period t that depends on this driving frequency. And now if we have such a system, we can apply Floquet theory and write down an evolution operator for one period of this periodic modulation. And this Hamiltonian will govern the stroboscopic evolution of our system. Now, it can be expressed in this form where this HF Hamiltonian is time independent. This means if we can find an expression for this HF Hamiltonian, we can try to engineer this periodic modulation in a way that this Hamiltonian has interesting properties, which are those, ideally, which we cannot emulate in a normal static lattice system. So then the game is to find a suitable periodic modulation of our system in order to generate the Hamiltonian we're interested in, and find a way to find an expression for this effective Hamiltonian, which we typically do in a high-frequency limit, because we can compute this Hamiltonian perturbatively.
What are some of the limits? How large or small capital T can be compared with 1 over small j in your original Hamiltonian? Because you have to worry about the spontaneous emission. You have your experiment is limited by some long time, right? So,
yes.
So to what extent does that affect the physics?
Well, so there are two things. So first of all, we want to make the driving frequency large compared to the hopping matrix element. For example, if we forget about interactions for now.
So
and then
omega is much, much larger than J.
it's much, much larger than J, exactly. And then this ratio basically gives you the proportionality constant for coupling to different Floquet states. So your experiment will be limited.
Is it 100G? I mean, I know nothing about the system. Is it 100? What is
I mean, it depends very much on the timescale of your experiment. For typical timescales that we have studied in our lab, it's maybe an order of magnitude. So a factor of 10 would already give you a very good result. And so these techniques have been used in several laboratories. And for example, it was used in a triangular lattice in order to study classical frustrated magnetism, because you can use it in order to flip the sign of one of these tunneling matrix elements of one of these bonds in a triangular lattice. And then there has been a whole bunch of experiments about artificial gauge fields and generating topological band structures. Of course, and I will focus on the technique that we have implemented in the lab, but there are many good review papers if you want to read more about the other experiments that have been done along these lines. And what interested me during the last couple of years was also to use the technique in order to engineer phases that cannot be accessed at all in static systems. So of course we have used this technique in order to engineer systems that otherwise are not accessible in our natural laboratory environment, but they have analogs, static analogs in condensed matter, for example, or in other systems. But you can also think about using this driving technique in order to engineer phases that otherwise would not exist in a static laboratory experiment. And for example, there are anomalous Floquet topological insulators, which are characterized by topologically trivial bulk energy bands. Nonetheless, they show topologically protected edge modes in the system. So that's one example of such Floquet-only phases. And this is the outline of my talk. So I will basically start giving you a brief overview of how we engineer artificial gauge fields and topological band structures in our optical lattice potential. And then I'm going to talk about some recent results, or to give you an idea about the understanding that we have at the moment about how we can include interactions and engineer topological many-body phases. And in the end, I would like to show you some recent results where we have tried to go beyond static gauge fields that we engineer using this driving technique and make the gauge field inherently dynamic. So engineering a coupling between matter and gauge fields where the gauge field itself has internal degrees of freedom. Okay. So again, I already mentioned that most of the experiments that we have performed were in the non-interacting regime, so we forget about the Hubbard interactions for now. We are working with a square lattice, which is characterized by real hopping matrix elements between neighboring sites. And now the first idea that one can think of to engineer topological band structures is to apply an artificial magnetic field, or for charged particles in such a potential, it would be applying a real magnetic field. Now, how does the Hamiltonian for such a system look like? Basically, it means that these tunneling matrix elements become complex. And we have these Peierls phase factors, which are nothing else but a discretized version of the Aharonov-Bohm phase that a particle picks up along a closed path. So it's connected to the vector potential that generates the magnetic field. And if we perform this integral around a closed loop, or if we think about a particle that hops around this closed loop, it will pick up a finite phase that is given by the sum of all these Peierls phase factors. And this phase the particle picks up, we can then interpret as a magnetic flux piercing the unit cell. So this is the phase which is given in ratio of the magnetic flux over the magnetic flux quantum. Now all we need to do is find a way, or periodic driving, that allows us to make these hopping matrix elements complex. And then actually one nice thing to mention here is that if we manage to engineer these phases on the order of 2 pi, or on the order of pi, we can generate very large magnetic fields that are on the order of 1 magnetic flux quantum, which allows us to access the physics of the Hofstadter butterfly. Now, just in a nutshell, how the technique works that we have implemented in the lab, explained on a 2-side model. We have site A and B. There's an energy offset delta between these two neighboring sites. And if this energy offset is large compared to the hopping matrix element, basically all dynamics is frozen. And now what we can do is we can apply a periodic modulation to one of the two sites. For example, to site A, we modulate it with frequency omega. And now if this frequency of the driving field matches the energy offset between neighboring sites, we can induce resonant hopping between neighboring sites. And if we go now through this Floquet formalism and write down our inverse series expansion of the effective time-independent Floquet Hamiltonian, we find that the stroboscopic dynamics is given by this Hamiltonian. So we have a renormalized hopping matrix element that goes with the first Bessel function of the first kind. It depends on the ratio of the modulation amplitude over the driving frequency. And it has this complex term, which is basically the phase or the initial phase of the driving that was applied to our system. And that's exactly what we want. Now, if we make this phase vary in space, we can use it in order to engineer such non-zero phases if we perform this integral around a closed loop, which we can then interpret as a magnetic flux piercing the unit cell. And in 2D, this looks like that. We have two lattice axes along y and x. Along y, it's just a real tunneling matrix element, a normal lattice potential. And along x, we have on top of that an energy offset between neighboring sites, delta, which is generated by a linear potential gradient. And now again, if it's large compared to the hopping matrix element along this lattice axis, all the dynamics is frozen. And we can restore it by introducing a periodic modulation at this frequency. And this is exactly what we do. So basically, we shine in two additional laser beams that do not couple any internal states. They are far detuned from any internal atomic resonances. They have slightly different frequencies, so they interfere and create a local optical potential that is time-dependent and depends on this frequency difference between the two sites. So basically, if we write down the potential at each lattice site, we find that each lattice site is periodically modulated in time with a frequency that is given by the frequency difference between the two beams. And if we set it resonant with the energy offset between neighboring sites, we can restore tunneling and describe it according to our Floquet formalism, which gives us complex hopping matrix element. And this phase factor that shows up in this periodic modulation is given by the value of by the dependence or the angle between the two beams. So basically what happens is that these two beams interfere. They create a running wave diagonal across this square lattice. And this phase front or this running wave evolves according to the wave vector difference, delta k, times the position in the lattice. And this is what gives the phase factor here, where we can then directly read off the magnetic flux that is generated in this lattice potential. So just as a particular example, as we have engineered it in the lab, these are the phase fronts of this running wave at a particular point in time. And now you can simply read off from this plot how much the phase advances between neighboring sites. So here the phase front is the same as here, so it advanced by 2 pi. So in between neighboring sites, it did advance by pi over 2. And this is basically what sets the scale of the strength of the magnetic flux that has been engineered. And it's a purely geometric effect, so by changing the angle between the two, you can vary the flux that was generated. So this allows us to engineer a homogeneous magnetic field piercing a square lattice. And this is the famous Hofstadter model, now written in a form where along x, we have this lattice index m and complex hopping, where the phase advances by n times phi. So phi is the flux piercing one unit cell, n is the lattice index along y. So here's an example for a flux pi over 2 piercing one unit cell, where you see that the phase advances by pi over 2 between neighboring bonds along the y direction, and hopping along the y direction itself is real. Okay, so we have complex hopping along x and real hopping along y. Now, without interactions, this model has this very interesting single particle energy spectrum, which is known as the Hofstadter butterfly. And here we have the energy of the lowest tight binding band in units of the hopping matrix element. And along the vertical axis, we have the flux piercing one unit cell in units of the magnetic flux quantum. Now, this structure can be understood as follows. Since we have the gauge field present in our lattice, the symmetry is no longer given by the discrete translational symmetry of the lattice itself, but we have to take into account the gauge field as well. So in the case of flux pi over 2, this leads to an increase of the unit cell by a factor of 4. One can show that the magnetic unit cell which governs the new translational symmetries, always contains a flux of an integer number or integer multiple of 2 pi. So in our case, that's why it's 4 times larger. And this leads to the fact that now the unit cell has 4 non-equivalent sides, which means that the lowest tight binding band splits into 4 subbands. And this is what you can see here. So the flux pi over 2 in units of the magnetic flux quantum is the value 1 over 4. And the lowest tight binding band splits into 4 subbands. Now you can play this game for different ratios, and you find that in the end, you get this fractal Hofstadter butterfly structure for the energy spectrum. And in particular, we are interested here in the lowest energy band, which has a Chern-number of 1 and is topologically equivalent to the lowest Landau level. And just as a side remark, this value is also particularly nice in terms of flatless ratio, which means that the gap to the next higher lying energy band is much larger compared to the bandwidth of the lowest energy band, which should allow us to enter a strongly correlated regime even with small interactions. Okay, now I would like to mention a couple of other experiments in different systems because the ideas that were used in order to engineer gauge fields or topological band structures are very similar compared to the ones that we have implemented in our lab. For example, the Haldane model, which was implemented in the hexagonal optical lattice, can be generated by breaking time reversal symmetry if you take your lattice and circular shake it in space. And a similar idea has been implemented in photonics, where here this hexagonal lattice that you see is basically shown here in this front plane. If you follow these points, you see a hexagonal lattice structure. And the time axis in this picture goes in plane. And it is wiggly waveguides that you see. So all this is an array of waveguides. They are coupled, neighboring waveguides. And these wiggly arrows mean that you shake or your lattice in space. So that's the photonics analog of the atomic experiment. And this was used to also engineer the Haldane model very similarly to the atomic realization. And also in superconducting circuits, these ideas have been used. Here you see that the coupling between neighboring qubits is modulated in time with a frequency that is also resonant with the energy offset with a phase in order to engineer this complex hopping matrix elements, very similar to what we have used in our optical lattice experiments. And there are, of course, many other examples, which I cannot all mention here. This is just a small subset of those. Okay, so how can we actually measure the topological properties of the energy bands that we have engineered? And the idea is closely related to quantum Hall experiments in solid state. Here you see the definition of the Chern-number of one particular band with index mu, which is the integral over the Berry curvature that characterizes the geometric properties of the energy bands. And the integral is performed over the first Brillouin zone. The Berry curvature is defined here. It gives you the structure of the eigenstates, which are here the periodic Bloch functions in a periodic lattice potential. And what's nice about this expression is that you can see, you can define it for each position in momentum space across the Brillouin zone, and then you integrate it up in order to get the Chern-number that characterizes the topology of your energy band. Now with cold atoms, you can actually try to directly access this quantity and measure the Berry curvature momentum resolved. And this can be done, for example, by building small interferometers. So if you think about preparing a wave packet in momentum space, you can build an interferometer by using, for example, 2 different internal states that you translate differently in momentum space around a certain region. And now this interferometer, once you close it again, will encircle a certain region of your Brillouin zone that is characterized by Berry curvature. And the phase that you measure at the end of your interferometer will be directly related to this Berry curvature that is inside your interferometer, very much like the Aharonov-Bohm type experiment in real space, where you can build an interferometer, and if you split an electron wave packet around a certain region which is pierced by a magnetic flux, the phase that you read out of your interferometer will be related to the flux that is piercing your interferometer. And very similarly, this works in momentum space. There are other techniques, for example, state tomography, which has been used with fermionic atoms in a hexagonal lattice to map out the Berry curvature or the momentum-resolved Berry curvature in the first Brillouin zone of the honeycomb lattice. Here you see the blue regions are actually negative values, the red regions are positive values, and if you sum up all of these, you will find that in this case, the band is topologically trivial. Now, in a case where you make the honeycomb lattice topological, the sign of these barrier curvatures will flip. And there are many other experiments. Again, I cannot mention all of them, also in other systems like photonics or using synthetic dimensions where the Chern-number has been measured in Hall ribbons. This is just to give you an idea about what cold atoms can do as different observables, using different observables as compared to solid state systems.
Question.
Yeah.
So can you illustrate a little more about the state tomography? What do you actually measure?
Well, the idea is that for each momentum state, so this works very nicely for a two-band model. I don't know how to easily generate it for more than 2 bands. And then you can think about each k point as a 2x2 matrix that is characterizing your state, which for each of these k components, you can think about a little Bloch sphere that is characterized by angles phi and theta that characterize your state. And it then connects you to other k components. So basically how these phases evolve as a function of k will define the topology of the band. And now what you need to do is to find a way to measure these angles for each momentum component. And the way it works is you prepare a Fermi gas such that all the momentum states are populated. And to quench it to a topologically trivial system, ideally with very flat bands so that you don't get any contributions from the dispersion of these bands. And then this quench will lead to rotations on these individual Bloch spheres for each k component. And from these, you can then extract the angles theta and phi. And this allows us to reconstruct the geometric properties of the band. In our experiment, what we did was to apply a force to our atomic cloud and perform a transport experiment. So the idea is you load your cold atom cloud into the lowest energy band, and then you apply a force to it. Now, we know that if we do that, our atoms undergo Bloch oscillations, which are governed by the dispersion of the band. But in the case where the topological properties of the band are non-trivial and the barrier curvature is non-zero, there's an extra contribution to it, the anomalous velocity component, that is transverse to the applied force. So what we expected is, if we perform this experiment, basically we apply a force and we expect our atom cloud to move transverse to the force that we have applied. And if we fill all the momentum states in the lowest energy band, we can get rid of this contribution of the band velocity component. It averages to 0. There's no net movement along the direction of the force due to the symmetry of the band. And the transverse center of mass motion is simply proportional to the Chern-number of the band that we have populated. Yes?
So, but you would have this anomalous velocity whether or not you have the Chern-number. If you just have some
sure.
temperature.
Yes. Yes, definitely.
This is very old.
Yeah. So is this
yes.
specific to having the global Chern-number, or it's just the...
No, I mean, as you said, you will always get this non-trivial contribution. But if we compute the center of mass motion and if we populate all the momentum components, we directly get out the Chern-number of the corresponding band. Now, of course, you could perform like local measurements. You prepare a wave packet at a certain point in momentum space, and you try to extract the barrier curvature at a certain point in momentum space by doing these kind of measurements. Here, we already performed this integration by populating all the momentum components to directly get out the center of mass motion, which is then proportional to the Chern-number, since this is just the integral over the barrier curvature. But you're, of course, right that, I mean, even if in a topologically trivial band, you can get anomalous velocity components.
But you would have that 0 in this case?
In this case, yes, because if you populate all the momentum components, some of them experience a velocity component that goes to the left and the other one goes in the opposite direction. And then the center of mass motion would be proportional to 0.
Is that explicitly verified in these measurements, that you get 0 in that situation?
Yeah, we tried to do that by... Basically, we did the measurement in a trivial lattice geometry without any flux, and also in a configuration where the flux is staggered. So on average, it is 0. And in this case, it's a little bit more complicated because the two bands are not fully decoupled. They are connected. But nonetheless, we can show that the motion is actually 0 in this case because the combined topology of the two bands is trivial.
I meant experimentally. Theoretically, of course, it's very well understood.
Yeah, we did. Yeah, we did that. These two experiments. Yeah.
An even more trivial thing is what about anisotropic effective mass? That would cause acceleration to have a perpendicular component, not just displacement. So I guess you're.
Say that again. Sorry.
So if the effective mass is anisotropic, which it is, then the acceleration, not just if you apply force, then you get a component of acceleration that's perpendicular to the force as well. It's not entirely parallel to the force. So that's sort of, in a sense, faster in time than displacement because it's.
You mean in this case the contribution from the band velocity do not average to 0?
Okay, I don't know if it averages to 0 or not, but I'm just asking about.
Because
that's another perpendicular component. Its time dependence is different. It's actually faster in time because it's acceleration.
I mean, there are all sorts of deformation of the cloud if you take an in situ snapshot.
Right.
So this argument is only really about the center of mass.
Okay, so the other bit must cancel for the center of mass. So the center of mass you're saying does not accelerate. I guess I'm worried that the center of mass accelerates or not.
That it accelerates.
Because of the force. Well, it does accelerate along the force, obviously.
The lower band is completely filled. So it is an insulator, it's completely filled. Right? So the only thing that survives is this thing. Everything else goes away. Because it's completely filled band.
Okay, yeah.
It's not a single particle, it's a full band.
Yeah, but then what's the center of mass of a completely filled band?
If you integrate over K, all of that will go away.
Okay. I mean, it's just in terms of physical measurement, it's a cloud. So it's not an what's an insulator in a cloud? Maybe, okay, anyway, maybe we can come back to this at the
Yes,
end.
okay. There's one subtlety, of course. We are not working with fermions, so it's a bit... no.
There's no real field.
But still, so we are working with bosons where the temperature is large compared to the bandwidth of the lowest band. So it's like an incoherent mixture of all these momentum components. And the
temperature is very large. It's a rather complicated system.
well, the band is very flat, so the temperature is actually not that large. But yeah, so it should remain smaller than the gap to the next higher lying band, which we will actually see in a second that is changing dynamically during the experiment. So we had this simple formula where the center of mass motion is simply proportional to the Chern-number of the band. But now if we consider that there are also atoms populating higher bands, yes?
So actually, what is the reason for using bosons versus fermions?
Yes, so there's a very practical reason to that. This experiment is with rubidium atoms. And so that's why we only have bosons available. And yeah, it's not easy to change to fermions.
Working with a bosonic lab.
Well, you know that we have the potassium rubidium lab, so there we could work with fermions. But in this lab, that's not easy to do.
So in this case, the lower band is not fully occupied, it's actually partially occupied. But average occupation is the same for all Ks because.
Yes, exactly. Yes, exactly.
It's about the same. But it's
Exactly.
Not 1. It's not 1. It's less than 1. Okay, so there are plenty of empty spaces.
Well, what do you mean by empty spaces?
So K and occupation number for given
It's
K.
a boson. So they're always in any.
But the average
What is the average?
average occupation is the same for each momentum
Yeah,
component.
but what is it in number? What is it
Oh.
less than 1?
No, it's not less than 1. We have around 100 bosons per lattice site. So it's actually quite large. Yes.
Actually, maybe something that would help me. So can I just think of it as essentially this is a condensed phase? Like it's a coherent state of bosons?
So, well, let me, it probably helps if I just explain how the loading more or less works.
Very good, yeah.
So basically we start with a condensate in a topologically trivial two-dimensional square lattice. So it's condensed at momentum q equal to 0. And then we came up with a sequence in order to ramp across the topological phase transition by varying one of our lattice parameters. And basically, if you follow the dispersion, how it evolves when you change this parameter, if your boson remains at Q equals 0, condensed, basically they will not see anything of this topological phase transition because it has a gap closing point at some high values for the quasi-momentum, but the bosons remain at their energy minimum. Now, during this ramping process, we have heating going on. So actually there's scattering between the atoms. And this leads to a redistribution in momentum space. And by the end of this ramp, we have basically a population in the lowest band where all momentum components are populated. We don't have a condensate anymore, and even some of the atoms are in the higher lying bands. So the temperature is smaller than the band gap here, but it's sort of like in between.
Okay. I mean, the reason I was thinking about, because for bosons, it's not sufficient to just specify n of k to describe the state. This is a problem. Like from
yeah, so in the end, what we are saying is
coherent. Is there any coherence or not?
I mean, coherence would modify our experiment, but we really believe at the point where we do the experiment, we have an incoherent mixture of all these momentum states, and then we treat them fully independently.
Okay.
But coherences would change.
In case there might still be some coherence.
I mean, in principle, yes, but we didn't see any of that. So it would definitely modify the measurement, yes. Also, I mean, in some sense, we need this heating or the scattering because if you would have a fully coherent evolution, I think you cannot create anything topologically non-trivial. If you start with a topologically trivial state at condensed at Q equals 0 and you make your ramps, I think it would remain topologically trivial.
You just need very little coherence breaking in principle. It's just a few gap closing points. So you can get almost coherent. Yeah.
Yeah, so in our case, I'm quite sure it's not. Not the case.
That's good, okay.
Yeah, so if we have these higher band populations, basically it means that our center of mass motion will not be directly proportional to the Chern-number of the lowest band, but the slope with which the center of mass motion evolves will be smaller than 1, reduced by this population factor that characterizes the population in the different bands. And the reason for that is that the Chern-number of the middle band is -2, and the whole sum of Chern-numbers of all bands sum up to 0. So in the case where, for instance, you have an infinite temperature state, it looks as topologically trivial, and the center of mass motion would vanish. Okay, and this is how such an experiment result looks like. We measure the differential shift, which just means that we measure the center of mass evolution for magnetic fields that point in opposite directions. So we take a snapshot for magnetic field pointing up, a snapshot for magnetic field pointing down, and then we subtract the two in situ positions in order to measure the differential shift. And this is one such example of such raw images after subtraction. And we see that indeed there's this non-trivial center of mass evolution, but it rapidly saturates to a value where actually no non-trivial motion happens anymore. And this Bloch oscillation time, actually, if we give it in real Bloch oscillation periods, it means this is like 2 Bloch oscillation periods, the 50 milliseconds. So after 2 periods of our measurement, basically all the atoms are in this infinite temperature state. And we can track this population dynamics as a function of time when we perform this measurement, and we see that the population in the highest band, which are these black points, increases over time. This is the lowest band, so it starts off already with a fraction that is lower than 0.75, and it reaches a value of roughly 25%, and the middle band reaches a value of roughly 50%. So at this point, we have an infinite temperature state which looks topologically trivial. And these timescales that we see here directly match the center of mass motion that we have measured in the experiment. And if we combine all this knowledge, we find that, okay, it's consistent, and we get a Chern-number of 1 for the lowest band. The question is, why is this repopulation dynamics actually happening? And this is what I wanted to tell you in the second part of my talk. Now I'm actually taking a lot more time for the first part that I had planned originally, so I'm not sure what we are going to do after that. But the question that we ask ourselves is basically how we can use these techniques in order to make or to engineer topological many-body systems, including interactions in our system, because that's, of course, the interesting situation that we would like to study. And for these driven systems, of course, we expect that they do eventually heat up to infinite temperature because we can always absorb energy quanta from the drive, and re-emit energy quanta into the drive. The question is, we need to understand what are the characteristic timescales of these processes, and if we can find a way to make these processes small enough such that the system looks at least stable over the duration of our experiment. And there are a whole bunch of single particle processes that lead to heating in the system, which basically occurs if we think about transitions between the lowest vibrational band in the lattice and higher vibrational bands. So everything I've told you so far only happened in the lowest vibrational band of the lattice, but of course, if we apply a periodic drive to our system, there can be multi-photon processes that take us into higher bands of our optical lattice. However, they are pretty well understood, and we believe that we can always find stable regimes where these are negligible for the timescale of our experiment. The question is, what happens if we consider now scattering processes between the atoms? And I already started mentioning this a little bit, because also in the previous experiment that I described as non-interacting, the interaction between the particles is relatively small, but still considerable. So it still gives rise to physics in our lattice, and as I mentioned, we have a two-dimensional square lattice, but about 100 bosons on each side. And out-of-plane direction is weakly confined by a harmonic trap. So there are many energy levels that are very close in energy. And this means that if you have scattering between the atoms, there are always scattering resonances that can take you out of the band that you're interested in and populate higher bands in your subspace, but also populate higher momentum states perpendicular to your lattice. And this is described by this Floquet-Fermi's golden rule, which basically modifies Fermi's golden rule by taking into account that in Floquet systems, we are dealing with quasi-energies. So if we add multiples of h bar omega to our spectrum, we are in this folded Brillouin scheme back into our original band. So there can be multi-photon transitions that take us out of our Floquet subspace into higher Floquet subspaces because we have this infinite repetition of our spectra. So this is this delta M, which describes the multi-photon process. And the interaction basically couples then your initial state to some final Floquet state that can be in a different Floquet manifold. And if we incorporate this in our analysis of our experiment, it seems to describe rather well the timescales that we see. So here you see again the plot of the populations, the dynamics of the populations that we see during our measurement. Here's the measured populations. Here's the numerically calculated populations by taking into account the scattering processes between atoms. So this in our case seems to be really the explanation for why we see this very fast repopulation dynamics, which leads to an infinite temperature state after only a couple of Bloch oscillation periods. Now, the obvious solution to that would be to get rid of this basically continuum of modes perpendicular to the lattice, for example, by increasing the confinement in the out-of-plane direction and freeze this direction of motion. We haven't tried that yet. That's something that is on the to-do list. Again, because we were working with rubidium, it's not as easy to do because in the case where we use a three-dimensional lattice, that would be ideal for that. Hubbard interaction energy U is already dominating everything. And this basically means we find ourselves directly in a strongly correlated regime, which is just experimentally not yet very easy to access and study. Yeah.
So when you say that you have 100 atoms per side, those are tubes. So you're saying put a vertical lattice along the tubes, and then in that case, U would dominate everything.
Yes.
So you have to do it with fermions within no interaction.
Well, in principle, if U is very large, that's already the regime we are interested in. It's just with the access or the observables that we had available in the lab in order to study this system, it seemed a bit difficult to go further from there. It does not. Ideally, you would also want to have, for example, a Feshbach resonance that allows you to tune the interactions, because then you can first study, can we get rid of this heating mechanism, and then slowly increase the interaction in order to create some interesting many-body state. Yes, so I guess due to a lack of time, maybe I skip the second part and talk about the last section, dynamical gauge fields. Okay, so the most recent result we would like to, or I would like to show to you is we ask ourselves if we can use these driving techniques in order to make the gauge field dynamical, so have its own internal degrees of freedom. And this is, of course, interesting from many different perspectives because it would allow us to study lattice gauge theories which can be depicted in this form. So for instance, you have your matter waves characterized by psi that tunnel between vertices in a lattice geometry and interact with a gauge field that is characterized by this link operator U. And now if we want to engineer lattice gauge theory, we have to find ways to mimic this internal degrees of freedom of the gauge field and engineer the interactions between this gauge field and the matter field in a way that respects the symmetry of the model that we are interested in studying. And these lattice gauge theories first came up in the context of high energy physics because it allowed successful numerical studies of dealing with this problem. And it's basically already has the structure that we have in the lab if we can find ways to engineer these gauge field degrees of freedom. But of course, these models, they also naturally appear in the low energy degrees of freedom on condensed matter models. And the one that I'm talking about today is a C2 symmetric model, which is very interesting for topological quantum computation, also condensed matter physics. Now, as I already mentioned, the challenge is to find ways to engineer these internal degrees of freedom and the gauge field and to engineer the interaction in a way that respects the local symmetries. And so far, there have not been many experiments along these lines. There is the experiment with trapped ions where they emulated the Schwinger model with 4 ions in a digital realization. In terms of analog quantum simulation, there have been first experiments trying to make the gauge field density dependent, which is like a first step you could take in order to make this coupling between matter and gauge fields. But it does not yet implement a full gauge theory that also is characterized by the local symmetries of the gauge theory. Now, in our case, what we are trying to do is to use 2 particles in 2 different internal states, A and F, that interact with Hubbard interaction energy U if they are on the same side. And we would like to use periodic modulation at the Hubbard interaction energy strength in order to engineer a C2 lattice gauge theory, which basically has this form. So we have our A creation and annihilation operators that describe the motion of the A particle. And we have link operators, here tau x and tau z, which will be implemented by the F particle. And then these 2 terms come with strengths JA and JF, and I will explain in a second what these individual terms mean. So that's the same Hamiltonian again. For 1D C2 lattice gauge theory, we have a C2 charge that is associated with the parity of the occupation of the A particle on each side. We have a C2 gauge field, which is this link operator tau z, which will be implemented by the imbalance of the occupation of the F particle. So it will take different values depending on if the F particle sits on the left or the right side. And the basic matter gauge coupling between these 2 terms occurs with strength JA. And then we have an electric field term which has strength JF, which is also encoded in this link operator tau x, which, as I will explain in a second, will be basic tunneling of F particles in the lattice model. And just to tell you something about the symmetries of this model, so we can write down this local GJ symmetry operator, which is the product of the charge operator and the electric field operator on all the links that emanate from this side J. So this operator here commutes with the Hamiltonian, which means that if we prepare an eigenstate that is of this local symmetry operator, the eigenvalues are conserved during the dynamics. This is what will then also allow us to get a measure of how well the local symmetry is actually implemented in experiments. And in this case, it can take values of plus or minus 1. And the physical subspace that we are interested in is governed by Gauss' law, as in electrodynamics. Now, in the C2 version, we can write it in this following form. So basically, it means we are interested in states that are eigenstates of the GJ symmetry operator. And each state is then in a certain subspace of the full Hilbert space, and it's characterized by the locally conserved quantities. Yes?
So, question. So, for gauge theories, in principle, there is a notion of a pure gauge theory which would exist even without any matter.
Right.
So here, it's not an option, right? It's
No,
tied to the
here,
matter.
exactly. Here it's coupled to matter.
And is it really quantum field theory, or is it classical theory in some sense, where you impose a configuration, meaning that it's a... okay, maybe it's...
Yes.
The F fields fluctuate.
Well,
So the classical, because of the tunneling of the F particles, I guess what you're calling classical is if tau z, if there was no JF term, then the tau z would be frozen.
Maybe.
Okay,
Yeah.
I thought that's what you were saying. Okay.
Yeah, no.
Electric field term.
Sorry, say that
You
again.
have the electric field
Yes, we have the electric field term,
That's just the F particle.
which is tunneling of the F particle, exactly.
So that's the pure gauge one.
Well,
But it would exist without particles, but then right, it only exists if particles are present. There is no notion of pure gauge theory.
in this model, I think no. Yeah. But okay, so yeah, no. In this, well, if you have only the JF term, but then it's trivial, right?
Well, it fluctuates. It's trivial.
Well, I don't know. Maybe it's not trivial. But that would be the pure gauge theory in this case, right? Okay. So writing it in this form basically also tells us what are the basic coupling processes in this C2 lattice gauge theory. For instance, if we start with a particle on side J and the electric field initiated in a value +1, then it's coupled by the matter gauge field term to this state where the matter particle tunneled over to the right side, and at the same time it did flip the value of the electric field to -1. So that's the basic matter gauge coupling that occurs with strength JA that leaves these GJ values conserved. And now on top of that, we have an electric field term that comes with strength JF. And we interpret these GJ values as, if GJ is -1, as a static local background charge in this model. Okay, so now just to get some intuition about the physics, let's think about a 1D chain where we have only one matter particle and the electric field is initiated in all +1 values on each link. So we have this local static background charge at j equal to 0, where gj is equal to -1, and all the other locally conserved quantities are +1. Now we can study the dynamics of this system first numerically, just to get an idea about what's happening, as a function of this relative strength of the matter gauge coupling and the electric field term. And what we find is that if the electric field is very small, basically it does not impact the dynamics of our matter particle. We see that if we initiate it on j equal to 0, it just spreads and tunnels across the lattice as we would expect if we just start with a localized particle in a lattice and let it expand. Now in the limit where the electric field term is very large, so jf over ja is here equal to 2, we see a different behavior. The A particle or the matter particle basically remains bound to its initial site. And if we increase this ratio even more, it will actually remain localized on site j equal to 0. And intuitively, we can understand that because we know that the basic coupling process is hopping over A particle and changing the value of the electric field in between. But this costs an energy JF. So if you want, you can just think about it as a detuned tunnel oscillation to the neighboring site because it costs some energy in order to tunnel to the neighboring site. And that's basically what you see here. If we increase the electric field term to be much larger than JA. Okay, just very briefly how we implement it. Again, we use bosonic rubidium atoms in two different internal states, here with opposite magnetic moment. This is important because both of these two atoms see the same lattice potential, so the same hopping matrix element between neighboring sites, and they interact with an interaction energy U if they are on the same site. Now, in order to break the symmetry between these two particles, because one of them is used to engineer the matter field and one of them is used to engineer the gauge field, we introduce a magnetic field gradient, which introduces a state-dependent energy offset between neighboring sites. And in this case, it's equal to the interaction energy U, which we will discuss in a second. And then we will apply a periodic modulation at the frequency of the Hubbard interaction, which will then give rise to complex hopping matrix elements, which will be used for the engineering of the gauge theory. And just very briefly, you have seen this before in this model. Also, n-photon processes will be relevant, which means that the resonance condition now looks like that. Previously, we had that the driving frequency matches the energy difference, but you can also have this more general relation where we need multiple of the driving frequencies in order to bridge the energy gap between neighboring sites. And now in this case, the renormalization of the tunneling occurs with the Nu's order Bessel function as compared to the first order Bessel function that we had before. And also the phase factor is proportional to this n-photon process. And something that will be central to the implementation of the C2 lattice gauge theory, if we flip the sign of this energy offset, we also flip, or we introduce an additional pi phase shift for the hopping matrix element. This is just due to the properties of the Bessel function that appear in the derivation of the effective Hamiltonian. Okay, and this is a measurement of these processes. So let's just briefly see how the different terms come about. So in general, if you use this model and you now drive it at the resonance frequency, which is equal to the Hubbard interaction energy, you get all sorts of processes which are all density dependent. So the hopping matrix element and also the complex phase factor will depend on the position of the other particle, very generally. But now you can choose certain modulation parameters, which in our case means the initial phase of the driving that you apply. If it's either 0 or pi, we can use it in order to engineer the C2 lattice gauge theory. And the different terms can be understood as follows. If we look at the dynamics of the matter particle, the hopping matrix elements depends on if the F particle is on the right or on the left side of the double well system. So since we're driving at the resonant energy U, it's a one-photon process. So it's renormalized according to the first order Bessel function. And we get a pi phase shift between these two configurations because there's a flip in sign in the energy offset between neighboring sites. So here it has to bridge a gap plus U, while here it has to bridge a gap minus U. And this gives order to the phase shift. And this is central because this pi phase shift will allow us to write the Hamiltonian in this form. We basically now define this link operator tau c, which is either plus or minus 1, which directly reflects this pi phase shift that we have. And A dagger A is just a tunneling of the matter particle. And so the tau c, the link operator, is then the imbalance of the occupation of the F particle, depending on if it's on the left or the right side. Okay, now for the F particle, there are two different processes, either 0-photon or 2-photon processes, because if the A particle sits on the right, due to the state-dependent energy offset that we have applied, hopping is resonant, and we get this renormalization according to the 0-order Bessel function. In this case, we have to bridge a gap of 2 times the interaction energy. Okay, so in the end, the hopping of the F particle is simply renormalized by J0 and J2, depending on the position of the other particle, and we can write it in this form, which explicitly depends on the position of the other particle, but we can simplify that by choosing a certain modulation parameter where these two Bessel functions are the same. And if we do that, then we end up with the Hamiltonian that we wanted to engineer to begin with. That's the C2 lattice gauge theory Hamiltonian. And just to show you one outcome of this realization, we start our system in an initial state that is an eigenstate of the local symmetry operator. Remember that the local symmetry operator is the product of the charge operator, which is related to the occupation of A, and the electric field operator, which is basically the tunneling of the F particle. So if we want to initialize it in an eigenstate of this operator, we can do the following. We can localize the A particle, which is an eigenstate of the charge operator, and prepare the F particle in a symmetric superposition, which is an eigenstate of the electric field or the tunneling term operator. So in this case, these are the locally conserved quantities, g equal to -1 and g2 equal to +1. And the basic dynamics is, as in the 1D model, we expect that the A particle starts to tunnel between the two sides of this very simplified model, and also the electric field term will flip its internal states accordingly. And the amplitude of this process then depends on the ratio JF over GA, as I said, because they are detuned tunneling processes, essentially. And what we have access to in the experiment is the C2 charge, the expectation value of the C2 charge, which is the occupation of the A particle, and the C2 gauge field, which is the tau Z operator, which is basically the occupation of the other particle on each side. And if we follow the oscillations, we see this. Blue points, compared to the ideal theory, which is given in gray, we see that it's strongly damped and it has a faster oscillation. This is reproduced by our numerics of the full three-dimensional system. And basically, these deviations are due to the fact that we have double-whale systems decoupled from each other, but we have a three-dimensional array of those. And if we take out our measurements, they are averaged over all these double-whale realizations. And each individual double-whale has slightly different dynamics because we have a harmonic confinement on top of our lattice system. And this dephasing shows up in these damped oscillations that we see. But it's taken into account for these blue-shaded calculations that we performed. And if you look at the F particle, it basically remains flat. There are no dynamics. And this is a signature of the implementation of our model, because if we wouldn't try to constrain our dynamics with these local symmetries, we would expect oscillations that have a similar amplitude as the ones of the other particle. And that is so strongly suppressed as compared to the dynamics of the A particle is due to these gauge constraints that you have implemented.
So I have a question. This is a non-interacting model, right? Is the model
well, it's two particles that interact.
So why is the theoretical simulation, why is it so broad? I mean, what's determining the width of the theoretical simulation?
It's calibration errors in our lattice depth, in our, yes.
Because, I'm very interested in the averaging question. Okay?
Yes.
So it's all input parameter issue. That gives that large.
Yes. And, okay, so I will not go through the details of this, just to tell you, we can prepare interesting states here, which are not only living in one subsector in our physical space, but we can now prepare coherent superpositions of different subsectors and study their dynamics. But okay, I will not go through these details. Just to conclude about the gauge theory part is what can we learn now from this implementation and just a two-side model. So what did we actually do? And as I mentioned, our data is in good agreement with our simulations if we take into account the full three-dimensional system and the averaging over individual double-whale realizations. And we see non-trivial dynamics which resemble the ones of the ideal C2 lattice gauge theory that we wanted to implement. Now the question is, how well did we actually do our job? And this we can only answer by accessing the eigenvalues of the symmetry operator to be sure that actually the local symmetry constraints that we apply to our system are conserved. So what we want to do is access these observables, which we cannot do directly in the lab, but we can check them numerically. And there are several potential symmetry breaking terms that are important here, which is energy offsets between neighboring sites that break the symmetry, which we have due to our harmonic confinement. So we basically expect that the symmetry is nicely implemented for the central double whale, but it's broken if we consider double whales that are at the edge of our system. And of course, there are higher order Floquet corrections that may break, and they actually do break the symmetry of the model. So this is, as I mentioned, if we calculate our effective Floquet Hamiltonian, we do this in an expansion series and in powers of 1 over the driving frequency to the power of n. So these terms are never completely zero, and they, again, restrict the timescale of our measurement where the symmetry is actually conserved. And then we have extended Bose-Haber terms, which means due to these interacting particles, we have density-assisted tunneling processes that also give rise to a symmetry breaking. And if we compute that, I wanted to show you how sensitive it is to the Floquet parameters. If we drive the system slightly away from resonance, actually this is completely off resonant completely resonant, there are some corrections, then we see huge oscillations in the value of the local symmetry operator. So here the symmetry is explicitly broken, but it can be fine-tuned such that the symmetry is actually preserved for very long times. So there are various contributions that we studied in detail, which allow us to say something about how well we can engineer the local symmetry in our system. And with this, I would like to thank all the people that were involved in these projects, for, in particular the people that were working on the gauge field realization for a couple of years now, and also on the dynamical gauge fields, in particular Moritz and Christian Schweitzer, who is a PhD student in the lab, and our theory collaborations. And thank you very much for your time. I just, flash the summary slide for questions.
Hey, the talk ended just on time. Amazing.
Well, not quite,
Well, by
right?
design,
And I was cheating, so.
There are lots of questions, but I'm sure there are more questions, and you're willing to answer questions, right?
Sure, of course.
Even tough ones, right? Okay.
Of course.
Oh, Ian would have a tough question, I'm sure.
No. So if you just give up on having the complete preservation of your gauge in varying subspaces, is there a way to delete the atoms that happen to leave it? Like, is there some measurement you can do that for which the dynamics you want is dark, so you can just come along and delete things that have done bad things?
I'm not sure I fully understand. You mean like using some quantum Zeno in order to get rid of the...
Exactly.
Yeah. That's a tough question. I think it's very difficult because these higher order Floquet terms that break the symmetry of the model, they are not easy to distinguish from the other terms. It's like additional correlated hopping events.
Well, it's more thinking in other terms of the Hamiltonian, but in terms of your state space, right? So what are the states you allow to keep?
Well, the usual way how it's done for all these gauge theory ideas that we try to introduce energy penalties for these extra terms in order to make them less likely to appear. But in the Floquet scheme, that's not an independent parameter because it's the expansion in terms of 1 over the driving frequency dot. So there's not so much degree of freedom one can use in order to do that. But I think for these Floquet terms, fine-tuning is a very good choice. What's a bit more difficult are these density-dependent tunneling terms, which I don't quite know how to suppress them nicely.
Victor?
Yes.
Two questions. Maybe one, the first quick question is, can you look at the finite temperature dynamics of this, in principle, this gauge theories? So I don't know, maybe you discussed with your colleagues, theory colleagues, there might be some finite temperature transitions. Is it something that you thought about? So I think one issue is that there is this confinement, deconfinement transitions to finite temperature. Maybe there are some experts here who know more.
Yeah, I mean, finite temperature in this case still means we are still in only one vibrational band of the lattice, right? So it's finite temperature in the subspace.
Or what is that?
Well, I have trouble in this setting thinking about temperature because our goal is to prepare a certain physical initial state and then study the dynamics. Now, in terms of temperature, I'm not quite sure what it means if we prepare a finite temperature initial state.
Yeah, maybe if I may ask another quick question. So when you do write your gauge Hamiltonian, so
Yeah.
these taus, they're still built out of the operators of your matter particles, right? So they're basically occupation numbers.
Yes, so there are the operators, the A operators for the matter particle and the F operators for the gauge field particle, and then out of these F operators we construct the tau operators. Yes.
I see. So, but it's equivalent, identical. Your statement is identical to gauge theory, so it's not like you can just talk about a two-fluid model or something like that. So.
In this particular subspace, yes, which means that we use hardcore bosons. So if you would want to extend it to a 1D model, it means that we need hardcore interactions between AA and FF dynamics and only AF Hubbard interactions that are finite. And then, of course, to know if it actually really maps onto the gauge theory, it's exactly these terms I was talking about. It's an approximation, of course, that we only take into account the tunneling of F particles and this imbalance to construct tau x and tau z. But there are other processes one has to be careful that may occur which cannot be directly mapped onto these terms in the ideal model.
Is there any difficulty to go to 2D and that's settle?
It's actually to 2D to study, you mean theoretically or experimentally? Because experimentally it's already quite a challenge to go to 1D actually, because what we have studied is only a two-side model. And just to give you an idea, what's the main challenge with this approach is that you define the link operators in a way that depend on the two sides. So your building block cannot be simply connected in a 1D chain because you get trouble on the side where they overlap. Like you can easily construct building blocks that consist of three sides, where then the link operator lives in between. Then you can easily connect them to an extended system. But as soon as you define your building block in this way, where the link operator depends on the two sides, it's a bit challenging, and one has to play additional tricks in order to couple, for example, two chains of these double whales, which are like separate by one, shifted by one lattice constant.
Any other question? So I have a question. So both are experimental actually. So did you just say that you going even to four sides along a 1D chain will be very difficult? Is that what you just said? Or is it third side on the other direction?
No, I would say 4 sides is equally challenging as 20.
So that's what you said. That's what I thought you said. Okay. That's not good. Because that's not good at all. I thought that's what you said. Because I was going to say if you do 4 sides, I'll accept it as a field theory. 2 sides is a bit difficult. Okay. So 4 sides would be difficult for the same reason. If you can do 4, you can do 20.
Yes.
And my second question, also experimental, is this averaging question. Because one of the problems I'm having with all cold atom experiments is that to validate the results, you have to do huge amount of analog simulation, digital simulation, sorry. If I'm going to digital simulation anyway, I don't need you. I mean, I don't need you at all. I mean, this is a philosophical question.
I think you will be very, very happy to hear that on our experiment where we collaborate, we are now trying to get rid of the harmonic trap.
No, but this is something I think the community needs to think about very hard, right? This started with when I looked at the original Bose-Hubbard transition of Emmanuel's famous experiment. And Matthias Schroeder is a friend of mine, and I knew how much work Matthias had to put to understand what's going on. And,
yes.
and so the thing is, digital simulations are limited. As you know very well, limited in size, not limited in time. And so I think we need to think very hard how, so
yes.
eliminate a harmonic trap
yes.
would be very
That's
good.
one thing I think
in
that
our
is
work,
very
you
important.
know how big an issue that has become. And here also you have to do this
yes.
time-dependent simulation. And I think that we need to maybe choose problems also. So you think some of these experiments can be done without the harmonic trap?
I think so, yeah.
Okay. All right. On that optimistic note, let's thank you.